Well, hi guys. In this session we're going to use Moivre's theorem to solve equations of the type z to the n equals a, where a could be any complex number. So let's go. We've got three equations here to solve, and you'll notice that they're all of that form. Z to the n equals a, where a could be real or could be complex, okay? This is a marvellous technique. You're going to love it. So let's get into it. Part A, we've got z cubed equals 1. We want the cube roots of 1. Now, you're used to there being one cube root of 1, which is just the number 1 itself. However, because of the fundamental theorem of algebra, we know that for a cubic, we would have three factors, and therefore, if we're solving that cubic equal to 0, we would find three roots, okay? And we know that those roots would either be real or complex conjugate pairs, okay? We know that. So z cubed equals 1, and we can rewrite that as 1 cis, in polar form, 1 cis 0 plus 2k pi, where k is any integer. That means any number of multiples of 2 pi, okay, either positive or negative. This is like a general solution statement, which can give us infinite number of solutions, okay? There will be only three unique solutions, however, for this cubic, as we would expect. After the third unique solution is found, the solutions start repeating. That is, they're not unique anymore. They start repeating what we've already found, okay? All the solutions to z to the n equals a will be spread at equal angles apart around the Argand diagram. Now let's continue on. By Moivre's theorem, we know that if z cubed equals 1 cis 0 plus 2k pi, therefore z would be 1 to the third cis of 2k pi over 3. Now all that remains is for us to substitute some values of k to find our three unique solutions. I always start with 0, and then from there I'd go 1 and 2. So when k is 0, we've got z is 1 cis 0. When k is 1, we've got z is 1 cis 2 pi on 3. And if k is 2, we would have z equal to 1 cis 4 pi on 3, which, if we put that in principal argument form, it would have to be 1 cis of minus 2 pi on 3, wouldn't it? If k is 3, now they're going to start repeating now. If k is 3, z would be 1 cis 2 pi, wouldn't it? Okay, but that is the same as 1 cis 0, which we've already found over here, you see? So they start repeating. Yes, that's right. Hence, if z cubed equals 1, we've got z1 is 1, which is 1 cis 0, and we've found that z2 is cis 2 pi on 3, and z3 is cis minus 2 pi on 3, and we can draw that on our Argand diagram as follows. There's z cubed equals 1, okay, 1 cis 0. There's one of the cube roots. z1 is 1 cis 0, which is 1. That's the one we're all familiar with. If x cubed equals 1, we would say that x would be 1, yeah? Here is the second one. z2 is 1 cis 2 pi on 3, and there is the third one, z3 is 1 cis minus 2 pi on 3. In other words, the radius from the origin here, out here, is 1 unit long, and the angles are, as we know, okay, 2 pi on 3, that means anti-clockwise from the positive direction of the x-axis, and for this one, it's clockwise, okay, negative angle direction from the positive direction of the x-axis. This angle is 2 pi on 3, that angle is 2 pi on 3, and that angle is 2 pi on 3. And we have the cube roots equally spaced around the Argand diagram. Isn't it amazing? It's absolutely amazing. This one here is our real solution. That's a real one on the x-axis, and it has no imaginary part. You see that? These ones are complex conjugate pairs. They are reflected about the x-axis. I know, it's incredible. So there it is. There's the answer to Mr. A today.